one is Nate Criss, and he's going to tell us all about his Commodore 128. So, and how he had, how his experimentation with that early in life. Well, we'll let him tell him, because I don't want to oversell and then like say, oh, he's going to tell us how he does his whole data center is based off of a 56K modem that he had. No, actually had 2,400 baud, 300 baud. How many baud?
This is a 300 baud.
So yeah, he designed whole data centers now off of 300 baud modem. That's how it works now. Because anyway, so I'll pass it over to Nate and let him entertain you guys. So, all right, thank you, Nate.
Hi, everyone. I'm going to pull up my slide deck here. If I can get the mouse cursor over on the screen. Yeah. My name's Nate Criss. I'm a network engineer. I'm based out of Muncie. The company I work for is actually based out of St. Louis. I'm actually a network architect these days, less of an engineer, more design. Wanted to talk about, when Criss told me that the concept for today was experimentation, I started thinking about when I was younger, much younger. I'm an old graybeard today, but I wanted to talk about some of the experimentations that have, some of the experiments and experiences that have stuck with me throughout my career from earlier on. There's a couple different types of experimentation that we can talk about. The first one I want to talk about today is the playful, creative experimentation. This, I think that a lot of people undervalue this type of experimentation. This is something that you can use to create a sense of intuition about some of the things that you're going to be working on in your professional career. This is also something that, you know, I would say doesn't necessarily require linear thought. You can just mindstorm and just think about the possibilities. And the other really nice thing about this is that there's no need to be afraid of failure. Sometimes the failure can be the most fun part of these types of experiments. The next type of experimentation that we're going to talk about is the methodical experimentation, which comes with troubleshooting. This is where I actually spend most of my time in these days. Either it's troubleshooting designs beforehand or troubleshooting designs after they go into production. You know, it's very much related to the scientific method that we're probably all aware of. You know, you start top down, bottom up. But what I found is if you can spend some of your time labbing things in your home, doing, reading about things, or just playing with different technologies that may be unrelated to what you're working with, you can build a sense of intuition to where you can maybe skip some of those steps and hone in on where problems are, and then use that to find a solution quicker than you would have otherwise going through all of the steps. So I really hope that today you get a sense of what experimentation can bring to you. Both of these are very useful, and like I said, I wanted you to think that they are not mutually exclusive. They can go hand in hand. And a lot of creative teams are built around people that have both skill sets, or some people that are stronger in one skill set or the other. But these types of critical thinking and abstract thinking are very valuable. The first experiment I want to talk about today is a Commodore 64, and a modem. This was me when I was about 10, 12 years old. It was when I got my first Commodore. And a couple birthdays after I got my Commodore, my parents got me a modem. And one of the things that when you're reading the manual of the modem, is like, okay, I need to learn how to dial phone numbers. And so a piece of historic trivia that this is all going away because everything is carried out of band these days, but one of the ways that old telephones worked when you dialed them is the numbers on the phone are based in a grid. And you'll see here, this is actually a page from the manual for the Commodore 1660 modem, is that it explains that the rows and columns have frequencies associated with them. So if you wanted to dial the number 5, what happens is the phone generates a 770 hertz frequency and overlays that on top of a 1336 hertz frequency. If you want to dial a 6, it does that same 770 hertz frequency, overlays that over the 1477, 0941 over 1336. You see how it works, but it just plays those two frequencies pretty much right on top of each other. So what I want to do right now is demo a little bit of how that dialing would work with a Commodore. I've got my 128 set up here. So the first tone that you heard was, column 2, row 3, which was an 8. Then you heard row 2, column 3, which was a 6. Row 3, column 1, which was a 7. Row 2, column 2, which was a 3. Or row 2, column 2 was a 5. So 8, 6, 7, 5. Probably some of you of my age can probably figure out the rest of the number that was dialed. So after I was reading this manual, what I realized was I was looking at the code that generated the touch tones, and I realized that it was similar to some other code I'd seen in magazines and manuals before. The number I'm going to look at here is 54272, and you'll notice it over on this side as well. What that does is that initializes the sound interface device, or the SID chip in a Commodore. And then what you do is you initiate that by poking a number into that memory register. And the register and the number that you put in represents a tone. Now these are actually the numbers that represent the notes of the musical scale. So if you wanted to play a middle C, for instance, you would do a poke 54272 and then put 75 in there as the value, and it would play a middle C. So I was thinking about this, and I realized, hey, if I can generate these tones, can I play music over the phone with my Commodore? So, in order to be able to test this, I had to go to a neighbor's house, which happened to be my grandparents. So I spend a few days in the summer, maybe a week, maybe 2 weeks. I don't know how time in the 10-year-old, 12-year-old mind is not the same as time is for us today. So I spend all this time writing code, and then I'm finally ready. I hear the music playing on the speakers. I can hear it when I pick up the receiver at my house. I can hear it. So I run over to my grandparents' house. Now, they don't live just right next door. We lived out in the country. They were our closest neighbor, but they're still probably a quarter mile away. The easiest way to get there was a path through the woods. then saying hi to all the cows, because they were the ones who created the paths for us. The cows' names were, some of their names were April, Macy, and Moo. And yes, I did name Moo. I was creative enough to come up with this computer program, but that was the best name for a cow I could come up with. And so get over there, and then I finally get to my grandparents' house, and on the wall, they have a rotary dial phone. And I don't know if you guys have ever dialed a number with a rotary dial phone, but it takes forever because you move the dial over and you have to wait for it to return, and you do the same again. And a little more old telephone system trivia is that they don't dial numbers the same way that a touch tone does. When you do a rotary dial phone, what it does is it picks up and lets down the receiver multiple times to represent how many digits, to represent the digit you're dialing within a certain amount of time. So it just rapidly hits the receiver up and down, and that tells the phone switch upstream what number you're dialing. So I get there, and I dial the number, and ring, 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 ring. The modem doesn't pick up, so I'm a little distressed, but I'm a 10-year-old kid, so I still have determination. So I go back across the woods, I say hi to the cows again, I sit down, and I start listing my basic code that's doing all of this. And I look at it for a long time, and it should work. I don't know why it's not working. And so I'm looking through the manual, and what I actually noticed first was the clue is the picture on the front of the manual, which this is the box, but you'll see here the same thing. And inside, on the modem, there is a switch. One of the settings on the switch is O for originate. The other one is A for answer. So flip the switch back to A, and then I run back across the woods, jumping over creeks, falling down. There's also the hazard of electric fences that keep the cows in, which I forgot about a few times. So that brings us to me standing there, dialing that rotary phone. So, dial my home phone number, and then finally, I get to hear this. Okay, it wasn't exactly this song. It was probably Pachelbel's Canon or something that I got out of a manual. But this was way more fun. And now it gets kind of cringy, but that's part of it too. So, something I want to talk about next is, you're playing with these. You're not the only one that is. You're most likely not the only one that is having similar thoughts or similar ideas. You can almost always find a community of like-minded people out there. You probably noticed a couple of people on this slide. The person on the top left is Steve Jobs. The person on the right is Steve Wozniak, founders of Apple Computer. The guy in the middle is John Draper, who also went as Cap'n Crunch. The reason he went as he came by the name of Cap'n Crunch is he was one of the first people to discover that this little whistle that you could get at the bottom of a cereal box generated a tone at a specific frequency, which is 2600 hertz. That was able to, not only do phone systems dial by using these specific tones, they have other controls behind them at that point in time. That was the tone that was used to initiate long-distance dialing. And so he discovered by manipulating those tones that he could get free long-distance dialing. And then he created an electronic device called a blue box, which before Jobs and Woz were creating home computers, they were building these blue boxes and selling them in kind of a gray market. But that 2600 became kind of a hacker calling card. Alt 2600 back in the day was a news group that most hackers hung out in. 2600 magazine is still published today. On the back cover of 2600 magazine is always a picture of a payphone, kind of in homage to where that came from. Experiment 2 is going to be more the methodical type of experimentation. It is where you have a problem that you need to solve, but the only way to solve it is by ruling out certain possibilities. And back when I first was a freshman here at Ball State a long time ago, I got the greatest minimum wage job anyone could ever ask for. I was working for University Computing Services, and I was punching down network connections in dorms and in the classroom buildings and everything. So I was going down to the basement with a punch tool, just going around punching down connections. I was also very fortunate to be here at a time when the campus was rolling out Ethernet. There was an old serial-based network called ISN before that, but I was here at the time where they were making the migration from ISN to Ethernet. And Ethernet is one of the main worlds where I live in today, being a network engineer. And so this experience really shaped my career. Back in the day, they used hubs instead of switches. So I'm going to talk a little bit about how Ethernet hubs work. I'm not going to go into switches, that's out of the range of this, but we can talk about that later. But the way a hub works is if you send a message in one port, it gets broadcasted out every other port. This is called a broadcast domain and a bridge domain, both in this scenario. So everything that's attached to this hub receives the message that's coming in. And then any response goes to everything else attached to that hub. So on the left you have a Asante hub, which was the brand of hub that was used at the time. Now I'm remembering 12 and 24 ports. I couldn't find any images of those. On the left is a mail truck. And the reason that the mail truck is there is because that was the mode of transportation that was used by us at the time on campus. We would get in the mail truck with the steering wheel on the right side, which is the wrong side, and drive across campus. And so my boss is like, hey, we've got a building that's down on campus, the network's down, I need you to come help me troubleshoot. And I'm like, okay, so we get in the mail truck, he's driving, I'm in the back because there's only one seat in the mail truck, and there's actually a bucket that I sit on that was kind of in the middle. But so we get over to the building, and at the time, the buildings had network topologies kind of like this, where you would have a hub in what was called the MDF, or the main distribution frame, and which was always in the basement next to the boiler, almost always. So when you're punching down those connections, your back is against the boiler, and you're all dirty, and still the greatest minimum wage job you could ever ask for. But that hub actually connects to all the hubs on the other floors. These were called IDFs, or intermediary distribution frames. This terminology is still in use today. When you're talking about enterprise networks and everything, you'll hear those terms thrown around. So you'll notice that MDF hub doesn't actually connect to any other computers. It just connects to the other hubs, which then connects to computers. You'll also notice that this hub on the second floor, hub 2, actually feeds other hubs up above it, because there are things like distance limitation and the number of hubs that you can chain together. So a lot of times you would have hubs in the IDFs that fed other hubs as well. So the network is down, and we get there and we see that the lights are just solid on the hub in the MDF. There's nothing going on there, and it looks like the hub is bad. We unplug the hub, plug it back in, no solution there. Swap out the hub, still doesn't fix the problem. So that means there's something else going on. So we start unplugging the cables that go to that hub, and we unplug the ones that feed the first floor, the second floor, and no change. But then when we unplug this third cable that goes to the second floor hub that feeds the other hubs, lights start blinking again. We can tell traffic is flowing. So that tells us everything's up above. So I get a walkie-talkie in my hand. My boss gets a walkie-talkie in his hand. He goes upstairs talking to me on the walkie-talkie, asking me what lights are looking like. Because what we're doing now is we're just iterating. We're doing the same experiment over, but we're doing it in a different location. So we get there, and he unplugs one cable. It doesn't work. Unplugs another cable. Hey, everything starts working. Now, you never want to stop when things start working, because you may not have the complete answer. Especially when troubleshooting, you want to look at all the possibilities. So if there's extra cables, you would go on and keep unplugging those to see if there's any difference. So we get up to where we isolate the problem to a single hub, and we see, hey, we unplug the first cable, nothing happens. We unplug the second cable, hey, everything's working. We plug that back in, things break again. Unplug the third cable, things start working. That's weird. So it's not just a bad device on the other side. Or not just one bad connection. Plug it back in, and then we go down the line, and we find out that those two are the only ones that are bad. It turns out that this wasn't the actual network topology that we were dealing with. Somebody had added an extra computer in their office and their own hub, and when they plugged their hub in, they thought, hey, I can get redundancy, I can get extra bandwidth or whatever by plugging two cables into my feeder hub. And the problem is we're dealing with hubs at the time. So remember how when everything that goes in one port goes out, comes back out in the other port and goes back out the other ports, and so you've got this loop. And it just starts creating a bunch of packets. The way to think about this, I read a great explanation about this that called this the Sorcerer's Apprentice syndrome. If you've ever seen Fantasia and you see Mickey Mouse and he's there and he's creating the brooms that have the water. So what's happening is this hub is just being Mickey Mouse in that scenario, and the frames that it's sending out are those brooms with the water, and it's just flooding the network, and the network can't do anything. It can't pass any traffic. So that was the actual cause of the problem, but you saw how experimentation brought us to the diagnosis and to the solution. Another important thing with experimentation is, can you repeat this? Can you prove that this was the problem? So I want to show you today what a loop looks like in practice. So this, I've got a Raspberry Pi back here, I've got my laptop connected to an Ethernet hub, then I've got another hub connected to a hub, and then I've got a Raspberry Pi in another hub. So what I'm doing is I'm just pinging that Raspberry Pi right now. And we're going to look at some stats and see what things look like. So 20 packets transmitted, 20 received, 0% packet loss. Hey, that looks good. So start the ping over again. And now we'll create a loop. And you'll see what's happening here. And you'll notice the dupe. So it's detecting a bunch of duplicate packets. How many duplicate packets? Like how many little brooms is Mickey Mouse creating in just that small amount of time? That was 19,283 duplicate frames on that network in just that small amount of time between two workstations. So you can imagine in a much larger network what kind of havoc this can release. Also in that amount of time, we had 43% packet loss because that's how bad the network was, and we'd see that going. It would eventually get to 99% packet loss if we left it running like that. I forgot the slide. Sorry. For any Headsucker Posse fan, movie fans out there. So, in the theme of having other people that are working on similar problems, I want to introduce you to Radia Perlman. She's the inventor of spanning tree protocol. And this is a problem that a lot of people were trying to solve for a long time. Her boss, I think she was working at Xerox at the time. I don't think she was yet at Sun. But her boss comes to her and says, hey, we're working on this problem. She goes home over a weekend, figures it out in a weekend. And so she came up with a mathematical formula to determine where there are loops in the network, and if there are loops, to shut that down. This work has been built on over the years. It's still in place. We try to avoid using it as architects when we can, just because there's some inherent dangers in relying on this. But Radia is just a brilliant person, and is one of the people that I would love to just spend an hour with talking and understanding how her mind works. You can see her motto here: the world would be a better place if more engineers like me hated technology. The stuff I design, if I'm successful, nobody will ever notice it. Things will just work and will be self-managing. And I think that is something that a lot of us strive for, and she's just brilliant. So the reason that we avoid using spanning tree in practice today is there can still be problems. The most common problem we see is the process that controls spanning tree will fail on an Ethernet switch, and when it fails, it is catastrophic. If you look at the image on the left here, you'll see that this is a Homeland Security report about a large telecom provider that had a 37-hour outage last year. This was so significant that we thought we were under cyber attack. What had happened was it was a switch failure, and they had a layer 2 loop in their network. I'm dealing with software-defined networking these days as my main focus, and I'm reading the manual for one of the software-defined networking packages that we use, Cisco ACI, and I come across this quote that, hey, we act like a hub in regards to spanning tree. And like, this is like high-end, super fast software-defined networking. It turns out that with emerging technologies, like what we're going to be experimenting with later on today with Particle I/O that uses mesh networking, loops are needed, especially in wireless, because it's how you get redundancy. And you can't always shut down like alternate links. A lot of times you have to be forwarding on all links to get the type of reliability that you need. So when dealing with new technology, a lot of times you get to revisit the problems that you have had with previous technologies because you now have better ways to address those problems. And that's something that I think we should always keep in mind, and why I thought the history lesson today was kind of apropos, because anything that you gain, no matter how old the technology, no matter how mundane the technology, that playfulness that you can tap in learning that may be valuable down the road, and most likely will be valuable down the road. My name's Nate Criss. I'm a network voice engineer, architect. You can reach me at Gmail, Twitter, LinkedIn. I have a GitHub repo and GitHub page. So thank you for your time. If you guys have any questions, let me know.